Here, in a continuation of 6.7, we will discuss composing inverse functions. We've discussed what a function is. We've also discussed what an inverse to a function is. And now we'll have a way to compose functions to determine if they are inverses of one another. So for instance, if f of x and g of x are each functions, and f of g of x equals g of f of x equals x, then f of x and g of x are inverses of one another. This says that the composition of a function and its inverse is essentially the identity function, which can be written as I of x equals x. Here is an example. Show that f of x equals 7x minus 2 and g of x equals 1/7 x plus 2 over 7 are inverses of each other. Step 1 would be to prove that f of g of x equals x. And step 2 would be to prove that g of f equals x. F of g of x is like saying f of let's keep it. F composed of 1/7 x plus 2/7, which looks like 7 times 1/7 x plus 2/7 minus 2. That simplifies to x plus 2 equals 2, or x. G of f of x is like writing g of 7x minus 2, which equals 1/7 7x minus 2 plus 2/7. Simplified, that equals x minus 2/7 plus 2/7, which equals x. So as you can see, both f of g equals x and g of f equals x. Thus we know the functions f of x and g of x are inverses of each other. An important thing to take note of would be that if both steps aren't satisfied, then either statement is untrue. Or if either statement is untrue, the functions are not inverses of one another. So we'll say that again. Both steps must be satisfied. If either statement is untrue, the functions are not inverses of each other. So both of these functions prove to be equal to x, so they're both true, and we know that the functions are inverses of each other. Lesson 6.8 covers graphing radical functions. Here we look at a function of x squared and a function of f of x equals the square root of x, and their corresponding graphs. Each graph of each function is known as its parent function, a basic function that has not been altered. We also have translations of each of these graphs or functions, which are different versions of the parent function that have been altered by adding operations. Here are some examples of translations that can be done on a radical function. We can reflect a function's graph in the x-axis. That would look like this: y equals negative square root of x. So the only thing that changed from the parent function to the translated function would be the negative sign in front of the square root sign. We can also translate horizontally using the variable h, and or vertically using the variable k. Y equals the square root of x minus h plus k. Notice that the horizontal translation is signified by an operation inside of the parentheses. So you're going to move in the direction opposite the sign, right or left, h units. The vertical translation is signified by the symbol outside the parentheses that tells us the direction of the translation, up or down, and the direction corresponds with the sign. So we say up or down in the same direction of the sign, with positive being up, k units, and if there were a negative there, we would go down k units vertically. As a note, it's important to know that functions can have both vertical and horizontal translations. You'll just have to be able to identify them in the function. So, is there a horizontal translation opposite the sign, or is there a vertical translation the same as the sign? Or there could be both.